isPrime. A classic use of for and while loops is in computing isPrime and nth prime. We'll start with isPrime, which is a fine application of a for loop. IsPrime of n will return true if the number n is prime and false otherwise. So it's going to take an integer, and if that integer is less than 2, we know that it's not prime in any case, so we'll just return false. Otherwise, what we're going to do is we're going to run a possible factor through every number from starting at 2, running up to, and not including n. That's what happens right here. You don't want to go all the way to n because every number is, in fact, a factor of itself. So we'll check 2, 3, 4, 5, 6, 7, all the way up to and not including n. If that number is in fact a factor, when you divide n by that number, you get 0 as a remainder, that's it. We found a factor, so this can't be prime, so go ahead and return false. If you make it through every single one of these, and none of them are factors, then that means it's prime, so we'll return true. So this is the pattern for isPrime. And we'll go ahead and test it by checking all the n in the range up to 100, and if it's prime, we'll print it out. And we see 2, 3, 5, 7, 11, 13, so forth. So this function works. What would have happened if we didn't do this test right here? What if we didn't have the special test if n is less than 2? Then we would have picked up that 0 and 1 are also prime, which is not true, of course. They're not prime. But why did that happen? Well, let's consider when n equals 0. We'll say for factor in range 2, 0. Well, range would cover all the numbers that starting at 2 up to and not including 0. There are no numbers in that range, so this does nothing, which means that this entire loop never executes, not even once. So we simply immediately return true. Same thing for 1. So in fact, the smallest value of n for which this loop will execute is 3, because even at 2 this doesn't execute. It just happens that 2 is prime, so that's fine. That's why we need the test right here. If n is less than 2, return false. It handles the cases of 0, 1, and also negative numbers. So that's isPrime. Let's go ahead and close this. We can do better though, and so we have faster isPrime. And there's several things we can do to speed this up. First, we can realize that we can handle even numbers very easily. 2 is, of course, prime. And if the number is not 2, but it is a multiple of 2, then naturally it's not prime. So these lines here take care of all the even numbers very quickly. So now all that's left are odd numbers, positive odd numbers. And for that, we're going to do actually much, much better. Not by getting rid of the evens, which was handy. It made things, faster for half-hard numbers, but by only going up to the square root. And there's a reason why. If we think about, for example, the number 24. 24 has which factors? Well, it has 1 and 2 and 3 and 4 and 6, 8, 12, and 24. Now these factors actually come in pairs. 1 times 24, 2 times 12, 3 times 8, and 4 times 6. Every factor comes in pairs. That's why you always have an even number of factors. But because they come in pairs, you always have one factor that's no larger than the square root, because it's multiplied by another factor that's no smaller than the square root. So because of this, we realize if we make it all the way up to the square root of the number we're considering, and we haven't found a factor by then, we can't find a factor after then, because it would have had to have multiplied by a factor smaller than the square root. So this is we don't have to save that, but this is an important change. Instead of going from 2 all the way up to n, we're going to go only up from 3 because we're doing odds, but basically only up to the square root of n. That's a very important change. And in fact, this code, by the way, which I'll modify in a moment, includes the int because it was written in Python 2. In Python 2, round returned it a float. In Python 3, round actually returns an int. There's no need for this int anymore, and we'll remove it. In any case, by only go up to the square root, we should be much faster. But first, let's make sure that we work equally well. We do. So now let's consider how much faster we are. So for that, we have the function prime, well, isPrime, and then we have the function faster isPrime, both exactly as written above. And now we're first going to verify that they have the same results. So we should go up to 100, but you can do a larger number in your own time. And then after they return the same results, we're going to actually time them by using a big prime number. 499 is not big, but Python is slow, so we'll stick with it. And we'll use in the time module, there's this function, time.time, and it doesn't return the current time in any really useful way. But if you call it and store the result, and you call it again and store the result, the difference between those two is the number of milliseconds that elapsed between the calls, and that is very useful. So we call time.time, then we call isPrime of that big prime, call time.time, there's the time it took. Then we do it again, time.time, but this time faster isPrime, call time.time, once again take the difference. And when we run this, we see that for 499, isPrime took 29 milliseconds, and faster isPrime on this computer took basically 1 millisecond. Let's go ahead and edit this code. We have some other prime numbers here that are bigger. So let's try this one. Go ahead and run this. And we'll see that well, it's a little slower now. But, oh, and it timed out. Aha! So Python is very handy for testing little things. It's not really good for testing things that are going to take a lot of cycles. They're going to run a long time. For that, you should copy it and should go ahead and run it in standard Python, which is what we're going to do here. So now this is standard Python, and we'll do the 499 again, and we see 0.12 milliseconds, much faster. And then faster isPrime is 0.016. So what is 0.128 over 0.016? It's 8 times faster. That's pretty good. But as these numbers get bigger, the wins get better. Now, it turns out that isPrime took 162 milliseconds, whereas faster isPrime still at only 0.07. And we'll go bigger yet, one more. And we'll put this one in here, and we'll run. And now 1568 versus 0.37. 1568 over 0.37. So now we're operating at over 4,000 times faster. So the larger the number you're looking at, the considerably faster isPrime will be. At this point, it's thousands of times faster. So it's certainly a win to use faster isPrime. It's worth going through all this to demonstrate this fact, because if you look at the code, isPrime is perfectly clear what's going on. Faster isPrime is maybe a little less clear. So there's a question of when is it appropriate to use less clear code to gain efficiencies, to run faster. And soon in the course, we're going to give you tools based on big O notation to analyze these functions and have a definitive answer. For now, we'll just casually say the difference in this case is thousands of times and growing. And that certainly justifies the increased complexity of faster isPrime. Finally, while you should use faster isPrime in your code, a couple of things to note, one of which is you should call it isPrime, not faster isPrime. That'll lead to clearer code. And you should understand how it works and not just copy and paste it out of the notes without thinking about how it works. You should definitely completely understand everything about faster isPrime and be able to generate it yourself easily from first principles.